Hello students, good morning. In this video we are going to see about diffraction. What is diffraction? Diffraction is a characteristics of all waves including sound waves. Diffraction is defined as the bending of waves around the sharp edges of an obstacle into the geometrically shadowed region. If you consider the bending of waves, this process is a violation to rectilinear propagation of light. We have already learned about rectilinear propagation of light. What do you mean by rectilinear propagation of light? Light always travels in straight line. But when light waves bend due to diffraction, this is a violation to rectilinear propagation of light. Diffraction is prominent only when the size of the obstacle which is diffracting the waves is comparable to the wavelength of the light. So, this is the reason why sound waves get diffracted prominently by obstacles like doors, windows, buildings, etc. The wavelength of sound waves is very large, comparable to the geometry of these obstacles. But diffraction of light is more pronounced when the obstacle size is of the order of wavelength of light. Diffraction in single slit. Let us consider a parallel beam of light falls on a slit AB. This is a slit. The width of the slit AB is small a. The S is a source of light. Light rays from the source is allowed to fall on the convex lens. After falling on the convex lens, a parallel beam of light is allowed to fall on the slit AB. The width of the slit is small a. For the parallel rays, the wavefront is plane. That is, when a plane wavefront is incident on a small slit AB, the waves get diffracted at the slit, and the diffracted beam falls on the screen kept at a distance d from the slit. The center of the slit is C. A straight line passing through C perpendicular to the plane of the slit meets the screen at the center O. Consider a point P on the screen. Consider a point P on the screen. All the light reaching at the point P from different points of the slit make an angle theta with the normal CO. All the light waves coming from different points of the slit interfere at the point P. The point P is a point on the screen and it gives resultant intensity. The point P is in the geometrically shadowed region. What do you mean by geometrically shadow region? It is the region up to which the central maximum is spread. Now we have to get the expression for path difference for the point to be minimum or maximum. So the basic idea for getting the maximum intensity, maximum or minimum at the point P is to divide the slit into even number of small parts for the minimum intensity at P, and for maxima at P, we have to divide the slit into odd number of parts. Let us see the condition for minimum first. Condition for the P to be the first minimum. Okay, so to consider the point P to be first minimum, we have to divide the slit AB into two equal halves, AC and CB. Now the width of each part is A by 2 because the total width of the slit is A. We have different points on the slit which are separated by the same width A by 2, and the points on the slit which are separated by the distance A by 2 are called as corresponding points. light waves coming from different corresponding points meet at the point P and they interfere destructively to make the point P minimum. Now the path difference delta between the waves from the corresponding points in such a cases, delta is equal to A by 2 sin theta. The condition for minimum is, first minimum is A by 2 sin theta is equal to lambda by 2 or A sin theta is equal to lambda. Now the condition for P to be second minimum. To get the second minimum at P, divide the slit AB into 4 equal parts. Now the width of each part is A by 4. We have also corresponding points here. The points on the successive slits separated by a distance A by 4 are called as corresponding points. Considering the light coming from corresponding points, the path difference delta between the waves from these corresponding points is delta is equal to A by 4 sin theta. For the point to be the second minimum, the A by 4 sin theta must be equal to lambda by 2. So A sin theta is equal to 2 lambda. Now condition for third minimum. To obtain the third minimum at the point, divide the slit into 6 equal parts. Now the condition for P to be third minimum is A by 6 sin theta is equal to lambda by 2 or A by sin theta, A sin theta is equal to 3 lambda. So the condition for first minimum at P is A sin theta is equal to lambda. The condition for second minimum at P is A sin theta is equal to 2 lambda. The condition for third minimum is A sin theta is equal to 3 lambda and so on. What is the condition for P to be the nth minimum? To get the condition for P to be the nth minimum, divide the slit into 2n number of parts, that is even number of equal parts makes the light produced by one of the corresponding points get cancelled by the counterpart. Now the condition for the nth minimum is A by 2n sin theta is equal to lambda by 2, or in general the condition for minimum is A sin theta is equal to n lambda, where n is equal to 1, 2, 3 etc., which is called as the order of diffraction minimum. Let us consider the condition for maxima. For points of maxima, we have to divide the slit into odd number of equal parts so that one part remains uncancelled, making the point P bright. The condition for first minimum is A by 2, A by 3 sin theta. Here we have to divide the slit into 3 equal parts so that the waves from 2 equal parts destruct to each other, and only the wave from the third part will produce maximum intensity at the point P. So A by 3 sin theta is equal to lambda by 2 or A sin theta is equal to 3 lambda by 2. The condition for second maxima is A sin theta is equal to 5 lambda by 2, because here we are dividing the slit into 5 equal parts. The condition for third minimum is A by 7 sin theta is equal to lambda by 2 or A sin theta is equal to 7 lambda by 2. In this case, we are dividing the slit into 7 equal parts. In the same way, the condition for nth maximum is A sin theta is equal to 2n plus 1 lambda by 2 for the nth maximum. Here n is equal to 0, 1, 2, 3 is called as order of diffraction maximum. The central maximum is called 0th order maximum. The points of maximum intensity lie nearly midway between the successive minima. Now we will see about Fresnel's distance. I've already seen that the rectilinear propagation of light is violated in diffraction, which is a bending of light. But this bending of light will not be seen till the diffracted ray crosses the central maximum. That is, this is a slit, and you know that at the this is the central maximum. It is being found experimentally diffraction will not take place until the light rays crosses a particular distance z from the central maxima, and this distance is called Fresnel's distance. In this distance, light ray optics is obeyed, and the light wave optics is not obeyed. That is, Fresnel's distance is the distance up to which ray optics is obeyed, and beyond which the ray optics is not obeyed, and beyond the Fresnel's distance only wave optics become significant. So in this diagram, this is the slit and this is the central maxima, and this is the geometrically shadowed region. Only in the region between this only ray optics is obeyed, and the distance from the slit up to this distance, that is the Fresnel's distance, ray optics, that is light will behave as a ray, beyond which only light will behave as a wave. So if you consider this diagram, theta represents the diffraction angle and z represents the Fresnel's distance, and A is the width of the slit. From the geometry of this figure, we can write A is equal to Z into 2 theta, or A is equal to Z into 2 theta. The diffraction equation for first minimum is A sin theta is equal to lambda, or sin theta is equal to lambda by A, when theta is small. So theta is equal to lambda by A. You know that A is equal to Z into 2 theta. From the definition for Fresnel's distance, 2 theta is equal to A by Z, or theta is equal to A by 2Z. You equate this theta and this theta, so you will get lambda by A is equal to A by 2Z, or Z is equal to A square by 2 lambda. After rearranging, we get Fresnel's distance Z is given by A square by 2Z. Now we are going to see the difference between interference and diffraction. It is difficult to find the difference between interference and diffraction because both were exhibited by wave nature of light. In the phenomena of interference, produce maxima and minima, and in the phenomena of interference, the principle of superposition is used, and in the phenomena of diffraction of light, bending of light takes place, and it takes place only in the geometrically shadowed region. Mainly the phenomena of interference, superposition principle is given importance, and in the phenomena of diffraction, bending of light is given importance. Now we can see the difference between interference and diffraction based on the appearance of the diffraction pattern on the screen. Let us now see the difference. The table gives you the difference between interference and diffraction based on the interference appearance of the diffraction pattern on the screen. Now interference, diffraction. In interference, equally spaced bright and dark fringes will be seen, but in diffraction, central bright fringe is double the size of other fringes. In interference, equal intensity will appear for all bright fringes, but in diffraction, interference falls rapidly for higher order fringes, and in interference, large number of fringes are formed, but in diffraction, only less number of fringes are obtained. These are the differences between interference and diffraction based on the appearance of the pattern on the screen. Now we are going to see about resolution. The phenomena of diffraction produces an adverse effect in the sharpness of the image formed in optical instruments. If you consider the diffraction, there will be a central maxima, and in the central maxima there will be a spread of the central maxima in the image for every point of the object, so that every point on the object acts as a point source. You know the condition for second central maxima or the first minimum produced by a rectangular slit. We have discussed so far as A sin theta is equal to lambda. But if you consider the slit to be a circular slit or a circular aperture, just like the convex lens used in an optical instrument, the diffraction pattern produced by a circular aperture, it will be not in the form of rectangular fringes. The diffraction pattern will be in the form of circular rings shown in this diagram, which are called as arrays discs. Most of the optical instruments form images of objects only through circular discs, slits. So in these cases, the diffraction effect produces an adverse effect. So in the case of a circular aperture producing circular images in diffraction, the condition for central maximum or first minimum is found to be of this equation: a sin theta is equal to 1.22 lambda. Here the numerical value 1.22 appears in the expression for central maximum or first minimum formed by circular slits. The expression derivation is not important in this case. So if you consider a circular slit and if in the case of diffraction pattern in circular slit, you can able to see arrays, rings like structures in diffraction. So in this case, for small angle sin theta is approximately equal to theta. So the above expression becomes a theta is equal to 1.22 lambda. This is for circular diffraction images. So rewriting further, I can write theta is equal to 1.22 lambda by a. From the geometry of this figure, if R0 is the smallest distance between the central maximum and the first minimum, then from the geometry of this diagram, theta is equal to R0 by f. Substituting theta from this equation in the first equation, we will get and rearranging, we will get R0 is equal to 1.22 lambda f by a. If you consider 2 point sources of light very close to each other form an image on the screen because of diffraction, the diffraction pattern of one point source may overlap with another point source producing a blurred image like this as shown in the diagram. Here we are using 2 point objects and it is producing diffraction using circular slit. Here the diffraction pattern of one will overlap with the other so that it produces a blurred image, not a clear image, or we can say it is an unresolved image. But to obtain a quality image or a well resolved image of the 2 point sources, the 2 point sources must be kept apart in such a way that the diffraction pattern of will not overlap with each other. You have to get a clear image here. So a scientist by name Rayleigh put forward a criterion which is called as a Rayleigh's criterion. According to Rayleigh's criterion, the 2 points on the image are said to be just resolved when the central maximum of one diffraction pattern coincides with the first minimum of the other and vice versa. So you will get a diffraction clear image here as shown in this diagram B. In other words, if the distance between the two central maxima must be at least R0. So only if the distance between the two central maxima is R0, we will get a well resolved image. This R0 is called spatial resolution given by the equation 7.54, which is R0 is equal to 1.22 lambda f by a, and the corresponding theta is called angular R0 is called spatial resolution and the corresponding angle theta is called angular resolution. It is shown that for better resolution, so from this it is clear that for better resolution, for R0 to be very small, the wavelength of light must be very small as possible and the size of the aperture A must be very large as possible. So only if the wavelength of light used is very small and the aperture size is very large, we will get the very well spatial resolution. The ability of an optical microscope to distinguish between two closely adjacent objects or 2 points on the screen on the same object is called resolving power of the instrument. In general, the term resolution is related to the quality of the image, and the term resolving power is associated with the ability of the optical instrument. Resolution and resolving power are both reciprocal to each other. Thank you.